Hello, students, and this is the second video. This is for section 6.1 for hypothesis tests. I think it's called 6.1-HT for hypothesis tests. So let's get to it. I'll show you the actual section that we'll be covering today. This should be a shorter meeting than the last one. The last one tended to be kind of long, but this one should be shorter. Certainly less than an hour, hopefully much less than that. All right, so let me share the screen with you, find the actual, see it? So just give me a second here and let me find it. Just give me 1 second here. All right. So I think it'll work now. Here we go. All right, so here's the section here, 6.1 HT, hypothesis test for proportion. Now, we've already talked about hypothesis tests. We've introduced them in chapter 4 and also in section 5.1 in chapter 5. I started introducing to you the steps of a hypothesis test, starting in chapter 4, but I went through 6 steps in chapter 5, and we talked about the normal distribution. And what's new about this particular section with hypothesis tests is that the test statistic, the z-statistic, which has a standard error in the denominator, we're going to replace the standard error that was chosen from Stackey. Remember, we used the randomization hypothesis test, and we chose or at least the Locke textbook chooses the standard error mentioned there. Instead of having the standard error used from a randomization hypothesis test, which is simulated, we're going to use an actual formula. Now, the formula comes from where? It comes from the last section that we talked about. The last video that I did, we talked about the standard error as p, the square root of p times 1 minus p divided by m. That's the standard error for a proportion. Now, what's different about a hypothesis test is that we have two hypotheses, as you remember, the null hypothesis, which is assumed to be true when we begin the test, and then the alternative hypothesis, which is typically the research hypothesis. And in addition, we have sample data. All right, we have sample data. So in case of a proportion, we'll have a sample proportion, p hat, typically it is, p hat. And in addition, of course, we have our hypothesized proportion for the null hypothesis. That's the value that's in the actual hypothesis. So in the book, it uses p sub 0, this right here, p sub 0, as the hypothesis from the null hypothesis, and p hat, of course, is your sample. I'm sorry, p sub 0 is the hypothesized proportion, and p hat is your sample proportion. All right. So the numerator is the same as it was in chapter 5. That's what we used before. We're going to replace this SE with, the standard error with, is that formula we talked about, which is that square root of p times 1 minus p divided by m. Now, this is what's very important. What we put inside the square root here is not the sample proportion, but the hypothesized proportion. That's the number that comes from the hypothesis test. So that's what we plug in for p here, p sub 0, the hypothesized proportion in the null hypothesis, 1 minus p sub 0 times divided by m. So the square root of all of that is our standard error. So our test statistic therefore becomes this. This is using a formula now. So now we've completely graduated from using Stackey, and we're now strictly using formulas for doing our hypothesis test. So our test statistic for a proportion, okay, because we're going to talk about this also in terms of means. Here, just in terms of her proportion, this is it right here. This is the formula. The numerator is p hat minus p sub 0. The denominator is p sub 0 times 1 minus p sub 0 divided by n. That's our standard screen. All right. Now, what are the 6 steps that we have to go through for a hypothesis test? Because that's really what I'm going to be talking about next. And then I'm going to go through some examples. All right. Now, the book has examples here too, but I'll go through examples at the back of this section for hypothesis tests, just to give you some examples. And then the examples will be good enough for you to do your homework, at least start the homework. Remember, as I'll tell you, as I told you in class, you get 3 attempts for your homework. If you're struggling with any homework problem, or maybe all of them, not really sure how it's going to end up for you, but just do at most 2 of the attempts. The homework will be due at a time after I get back. All right, I'll give you plenty of time to get your homework completed. All right, so try the homework. Again, listen to my video, read the book. In Wiley, under the modules for this particular section, there's videos there. There's things written up there for you. But if you're confused or you're not, unclear about most of this, don't worry about it. Just again, try it. And then when I get back, I'll clarify all the confusions that you may have. All right, so the best thing to do now is just to show you the 6 steps that you need to go through for a hypothesis test, and then do some examples. All right, so this is pretty much what we did in chapter 5, except now we have a complete formula for our test statistic. The steps are exactly the same as before, but we'll take a quick view of what those steps are. So get out of here and let me just make sure I have that PDF that I have. I have posted this PDF for you. So the PDF is basically the 6 steps. So let me share the screen with you for the 6 steps. There we go. This is the 6-step hypothesis test for a population proportion. Now again, just like we've done over the last couple of weeks for a hypothesis test, the very first step is to state the null and alternative hypothesis. Remember, it has to be done symbolically. I know that many students don't do this, especially in the final exam, but I could tell you very clearly that if you don't use the proper symbols in the final exam, the questions that relate to all of this, you'll get a 0 for it. Even if the idea is sort of there, you won't get any points. All right, so please do it exactly the way I'm showing you, exactly the way the book is showing you. Don't come up with your own way of writing it, or writing it in English, or doing whatever. It has to look like what I'm showing you. If it doesn't look that way, then it's not gonna, you're not gonna get any points. All right, so it's really key just to follow these steps, one step at a time. The step 1 is to state the null and alternative hypothesis. And remember, a hypothesis test, we never use the symbol for the sample statistic. In other words, in this case, the sample proportion. Use the population parameter, in this case, the population proportion. This is just an example of one right here, where the null hypothesis is p is equal to 0.72. Remember, the null hypothesis always has an equal sign in it. The alternative hypothesis says p is not equal to 0.72. And as you remember, this is a 2-tailed test, right? Just saying, we're just looking at whether p is 0.72 or something different than it. It could be less than it, it could be more than that. All right, now the second step, and again, this is something you must be very precise with, all right? I can't overemphasize this. If you're not precise, you leave things out, you get 0 in the final exam for these questions. So it could mean the difference between one grade and the next grade. Just follow the steps that I give you, all right? Just don't do what, just don't find shortcuts or say, oh, I don't feel like doing this. It's just doesn't work, all right? You have to do it in the way I'm teaching you. So the assumptions used for the hypothesis test, the very first assumption always has to be the sample was randomly selected. Because if there's no random selection, we can't use the normal distribution. We can't do any of this. We have to use some other method for doing a hypothesis test. So random selection is an assumption that's used. Now, in the final exam, they're going to say, what is the assumption? And then they're going to say something like, was it clearly stated in the problem? Well, the problem typically will state it, and you'll say yes. So you're going to write out what it is and say, yes, it was stated. You have to say both things, all right? So please read the question and answer it the way it's asked. Then we do this calculation. NP, what is N in this case here? N is the sample size. What is P? That's the hypothesized proportion. That's what you're going to put in here, not the sample proportion, the hypothesized proportion in the null hypothesis. So this example up here where it's 0.72, we would put 0.72 times whatever N is. So again, we have to take N times P and see if it's greater than or equal to 10, and also N times 1 minus P to see if it's greater than or equal to 10. So again, in the final exam, they're going to ask what are the assumptions. You're going to say assumption 1, that the sample was randomly selected, and then state whether it was clearly stated in the problem. And number 2, you're going to say state this assumption that's right here, and then through calculations. And please don't just say it. Show me the darn calculations. I don't mean to be kind of, a little hurt with you here, but just show the calculations. And how much trouble is that? I've seen students just not show anything and just say, yes, it was confirmed. No, you'll get 0 for that. You have to show the calculations. So you have to replace N with the number and P with the number and show that it's bigger than or equal to 10. The same thing with N times 1 minus P. All right. Need to show calculations. Please do it. How much time does it take? 3 seconds, 5 seconds? Just do it. And again, I feel so bad that I have to give zeros for these questions that you know, but you just don't feel like writing it down. You have to write it down to get points in the final exam. I'm telling you right now, you have to do it. Because if you don't do it, you get zeros. And I've seen people fail the final just because of that, and they lose an entire grade. Grade just drops by 1. It's not worth it. Just do the work. And then you can go out and have some fun after the final exam's over. All right? All right, so you have to do both of these. You have to state what they are and then confirm that they're true. All right? So that is a final exam requirement. Here's an example right here where if N, the sample size is 1,000, the hypothesized proportion 0.72, you notice it matches this 0.72 up here, then 1,000 times 0.72 is 720, that's bigger than 10. And then you can see the formulas being used here. You show the formula and then you replace those letters with the numbers. And then the next one's 280, that's greater than 10. And you could say yes, because both NP and N times 1 minus P are both greater than or equal to 10. The sampling distribution of sample proportions is approximately normal. All right, that's how you do it, exactly the way I just showed you there. All right, if you want to pass the final, you got to do stuff like this. Right? All right, let's look at the next third step. This is where we calculate the test statistic. Well, remember, in chapter 5, we use the standard error. The denominator here, this denominator was just whatever the randomization hypothesis test stated the standard errors, that's what we plugged in, but now we're going to calculate it. All right. Remember, in the denominator, we're using the hypothesized proportion in here instead of the sample portion. That's what we put into the square root. All right. Once we've calculated this Z star, which we can call the test statistic, we then calculate our p-value. Now in chapter 5, we did this, right, with normal CDF, right? Showed you how to do it. The only difference here is that we have full formula here for our test statistic. Everything else is the same. That's in chapter 5. So in here, we calculate our p-value. So again, we have the 3 types of tests. We have our two-tailed test, left-tailed test, right-tailed test. Remember, the two-tailed test says that our alternative hypothesis states P is not equal to, right? Some number, whatever that number is. P is not equal to. So we're looking for that not equal to. That's the two-tailed test. The left-tailed test would say P is less than in the alternative hypothesis. And for the right-tailed test, P is greater than some number, the alternative hypothesis. So this is just a review. For if it's a two-tailed test, that is, P is not equal to in the alternative hypothesis, remember the p-value is 2 times normal CDF, and we use Z star, okay, Z star here. We're going to use that test statistic inside here. Now notice that there's 2 different forms of it here, and the reason there's 2 forms is that if Z star happens to be negative, all right, if Z star happens to be, well, not, yeah, well, yes, if Z star happens to be negative, less than 0, okay, you know we're going to be using the left tail of the standard normal curve, right? So we're going to put it in this form here. And if Z star is, the test statistic is positive, we're going to use this form here. And of course, you know, in this form here, with in this form, where Z star is greater than 0, that's because it's a right tail. All right, remember, right tails we do Z is greater than Z star for our p-value, and then the one for Z star less than 0. That's we're going to use the left. Now we have to multiply by 2. Why? Because it's a two-tailed test, and we have to use both tails. All right, so when we find one tail, the other tail is going to be exactly the same. So we just double that area. We're using both areas, so both tails, and by doubling it, will give us our p-value. All right, so remember, two-tailed test, we double the normal CDF. All right. Okay. Now, if we have a left tail test, then we don't do doubling. The left tail is actually the p-value, right? Talked about this before. We use normal CDF and we put it into this form here where Z star is negative. If Z star, all right, because it typically will be negative, all right? But if it, you know, it doesn't have to be negative, but typically it is, all right? If we have a right tail test, again, you know, it depends on the direction of the greater than or less than, right? All right. So in this case here, a right tail test would be greater than, left tail test would be less than. That's for our alternative hypothesis. So if it's a right tail test, again, we don't double it. The right tail is going to be our p-value, right? The right tail area. So we use this formula. So remember, when we do our Z, our test statistics, we're getting a Z score. We're getting a, we're going to use the standard normal in our normal CDF to come up with our p-value. All right. And then step 5 is the decision rule. Once we've calculated the p-value, we determine if it's less than or equal to alpha, or probability of a type 1 error, right? Or the level of significance. These are all equivalent terms. If the p-value is less than or equal to alpha, we reject the null hypothesis. If p-value is greater than alpha, we do not reject the null hypothesis, right? That's the decision rule, just like before. And then we have our interpretation and we'll say at the S% significance level. So whatever the alpha is, we convert it to a percentage, and we put the number in here. And then we state whether there is enough or not enough evidence to reject the null, right? Again, if p-value is less than or equal to alpha, we're going to say reject the null in here. And if it's greater than alpha, we're not going to reject. But the important thing is when we do an interpretation, we put it in the context of the problem. All right. So we don't just say we reject the null. We're going to say we're going to reject, and we state what the null hypothesis is. We state it, right, in words. So an interpretation requires actual words. All right. Now, And that's what I said here. So those are the 6 steps. All right. So that's pretty much what you go through when you do a hypothesis test, those 6 steps. All right, so that was a review. Let's actually do some examples now. Just again, just like we did for chapter 5, this time we have complete formulas to use for our test statistic. All right, so let's go back to the book. All right, and let's look at the exercises. All right, so what I like to do is take a look at some of these exercises and see what they're asking, right? So we'll do some of the simple ones, and then we'll do a couple word problems and show you how the 6 steps work. And that'll be it for the video. All right, this again, just a review. All right, so let's look at 6.47. Let's read exactly what we're supposed to be doing here. We want to determine, first of all, is it appropriate use the normal distribution to estimate the p-value? In other words, we have to do that test. Is NP greater than or equal to 10, and is n times 1 minus p greater than or equal to 10? Let's look at 6.47. And notice that p, the null hypothesis is that p is equal to 0.3. And we can see that the alternative hypothesis is that p is less than 0.3. So I'm going to pause this just for a second. Stop sharing and pause. Okay, so just had a little bit of an interruption. Had to take a phone call, so apologize for that, but that happens. All right, so again, I'll share the screen, and let's go back to the book. All right, so this is 6.47, and what we have to do is we have to see if the normal distribution is appropriate. That is, we have to multiply n times p and n times 1 minus p. And then we're going to assume it's random sample. So there you go. I mean, it's telling you, assume it's from a random sample. That's one of the assumptions too. And it says use a 5% significance level. All right. So it says if it is appropriate, use the normal distribution and give the given sample results to complete the test of the hypothesis. We're going to do an actual hypothesis test here. So step number 1 is the null and alternative hypothesis, but they give it to you. All right. So lucky you. In this particular problem, 6.47, they tell you the null is equal. The null hypothesis is that p, the population proportion, is equal to 0.3, and the alternative is that p is less than 0.3. So this is going to be a left tail test. Know it for sure. We have to make sure the assumptions are met. Assumption 1, that it's a random sample, is true. All right, it says it in the problem. And the second assumption, well, we have to multiply our n times our p. Now, notice here they give you the sample results as p hat. Please do not use p hat to determine whether we can do the hypothesis test. And I'll tell you why. Because when you set up this whole research project and you're going to set up the hypotheses and all of that, you haven't done the research yet. You haven't acquired the sample statistics yet. All right. You don't even have the people yet who are going to be in the study. So the important thing is that p hat is something that occurs later. So this thing that we're doing now, the assumptions, this is something that we would do before we collected the data. So therefore, p hat doesn't exist. The only thing that we have is the null p, which is 0.3. So that's what we're going to multiply times n. Now, 200 times 0.3, we can do that in our head. That's 60. That's bigger than 10. Now, 1 minus p is 0.7. 200 times 0.7 is 140. That's also bigger than 10. And the answer is yes. That assumption that np and n times 1 minus p are bigger than 10. Both, it's true in this case. Both of them are well bigger than 10. So we'll do the actual hypothesis test. So we have, of course, that p is equal to 0.3, p is less than 0.3. So what is step number 3? Step number 3 is the test statistic. All right, so what do we know? We know in this case that p hat is 0.21. That's our sample proportion, and that's out of 200 people, right? We have 200 people. All right, so let's do our test statistic, and we're going to use our calculator to calculate. All right, so let's share the screen for the calculator. All right, so our test statistic, the numerator is going to be p hat minus our hypothesized p. So what I'm going to do is I'm going to just open up a set of parentheses. P hat is 0.21. That's our sample proportion, minus our hypothesized proportion is 0.3. Now, we do divide by, and what's our denominator? The square, it's our standard error, which is the square root. Now we use p, not p hat, inside here, so it's going to be 0.3 times 1 minus 0.3, but that's 0.7, all right? And divide by, and it's 200, sample size is 200. Okay, all right. Now we could use our arrow to exit out of the, right arrow to exit out of the square root. We can do that, hit enter. And there is our test statistic. It's negative 2.777. All right, with some other digits after that. Now, what I'm going to do is I'm going to store the test statistic in an alpha character, alpha A, right? So I have this number here. It's in memory. I'm going to do store alpha A, hit enter. And now my test statistics is now stored in our alpha A, all right? Now, what are we going to do next? Now, this is what type of test is this? So let's go back out. Let's go back to the problem. Okay. The next step is to do our p-value. So let's go back to Wiley Plus and look at the question. And 6.47 says the alternative hypothesis says that p is less than 0.3. That is our left tail test. Left tail test. So we're going to do a left tail test. Let's once again look at our document, 6 steps. And since it's a left tail test, let's see what the normal must look like. Step number 4, left tail test. Here's the left tail test. P-value is going to be normal CDF. We'll use negative 1,000 for the left endpoint. We're going to use our test statistic. The next number is going to be our test statistic. That's going to be a right endpoint. And then, of course, this is a Z, so our mean is 0, standard deviation 1. Okay, so let's go back to the calculator and actually do this. All right, so we're going to pick normal CDF. Now remember, this is left tail, so we're not going to multiply by 2 like a 2-tailed test. And again, we're going to use negative 1,000 here for the left. Now, because we stored our test statistic in alpha A, we're going to recall that alpha A here, right? Or we could just simply type it in. Why don't we just type in alpha A? Right? It knows it's an alpha A. All right, we could recall it if we wanted to. There's no reason to recall it. We could just type in alpha A. And then scroll down. Now, the people who are have the 83 calculator, just you could store it, all right, and you should store it, but you're going to put everything in parentheses. In other words, it's going to look like this. As long as you've stored the number in the test statistic in A, this is what you're going to type in inside the parentheses for the normal CDF. And this, ladies and gentlemen, is the p-value, 0.0027. Okay, that's our p-value. Now, if you go back to the problem, stop sharing, go back to the problem. Okay, Once we have our p-value, we'd have our decision rule. Now, this is a small p-value, 0.0027. Go back to the book. Notice in the problem, it says assume or use a 5% significance level. 0.0027 is well below 0.05. Therefore, we're going to reject the null hypothesis. All right. Now, we're not that's step 5. We're going to reject the null hypothesis. We can't really do an interpretation here because you don't have any information about this particular test, right? There's no context to it. It's not a word problem. So step 6 we can't really do. But if there was a word problem, step 6 would just basically be saying something like, at the 5% significance level, we have enough evidence to reject the null hypothesis, which is, and then you write what it is, right? Something like that. All right, so that you have to put it in context. All right, and then they have some other ones here. Let's see if they have a two-tailed test. Well, this is left tail. Let's look at 649. 649 shows that the null hypothesis is equal to 0.8. Okay. And the alternative hypothesis is p is greater than 0.8. Okay, so it's the right tail test. And then notice that p hat is equal to 0.88 with a sample size of 50. Okay. Sample size of 50. So let's go actually to the calculator and make sure that n times p and n times 1 minus p are both bigger than 10. Okay. Otherwise, we can't do the actual test. All right, so let's go back to the calculator. Do that first. And let's just erase or clear out the screen. So we're going to do n times p. Now, remember, p in this case is 0.8. That's the actual null hypothesized value. That's what we're going to use. So 50 times 0.8 is n times p. That's 40. That's bigger than 10. And then 50 times 0.2. That's 1 minus p. That's 10. Well, that is greater than or equal to 10, right? So we barely, n times 1 minus p is barely good enough, all right? Remember, n times 1 minus p and n times p both have to be greater than or equal to 10. And in this case, it is equal to 10, so it's barely good enough. We can do the hypothesis test. All right, since we can do the hypothesis test, let's actually calculate the test statistic in this case here. All right, so I'll clear out the screen again. And again, we'll open up a set of parentheses, and it's in the numerator of the test statistics, it's going to be p hat minus p. P hat is 0.88. And then p, the hypothesized proportion, is 0.8. Divide by, and then we do the square root of p, which is 0.8, times 1 minus p, which is 0.2, divided by the sample size, which is 50. And the answer is 1.414. But again, we don't need to round it or anything. We're just going to store that now into alpha A. Because we have a new problem now. We can literally keep using alpha A over and over again. You can use other letters if you want. So I'm going to hit the store button and store that into alpha A. Hit enter. All right. And this way I can use it in my normal CDF. Now, this is a right tail test because the alternative hypothesis says p is greater than positive 0.8. Greater than 0.8. All right. So we're going to use normal CDF. Now remember, right tail test, you don't need to multiply the normal CDF by 2. In this case, this is a right tail test. Our A will go into the lower, alpha A here, and then we'll use positive 1,000. It's the right tail. And scroll down and enter. That's what you would type in if you are using an 83 calculator. And there's our p-value, 0.0786. Now remember, these problems here are saying that the level of significance is 0.05, 5%. And this number, 0.0786, is bigger than 0.05. So in this case, we will not reject the null hypothesis. We do not reject it. All right, let's go back to the book. We'll do a two-tail case. And look at problem 6.51. In this case, the null hypothesis says the population hypothesized proportion is 0.2. And then the alternative is that it's not equal to 0.2. Notice that p hat in this case here is 0.26. And we have a sample size of 1,000. Okay. So once again, we're going to do our NP times n times 1 minus p to ensure that we can, let's just write this down, just give me a second here. N times p and n times 1 minus p, we want to make sure that it's at least equal to 10. Go back to our calculator, and I think they are. I don't think we need to, but we still have to do the calculation. So let's just do it, clear it out. All right, so n in this case is 1,000, and the hypothesized proportion is 0.2. It's 200, so that's well above 10. And then 1,000 times 1 minus p, which is equal to 0.8. That is equal to 800. Again, way bigger than 10. So we can use the normal distribution, the normal CDF, to calculate our p-value. All right, so let's go ahead and do that. Let's calculate. First of all, we have to calculate our test statistic. So, oops, sorry about that. That's what I wanted to do. Let's clear this out. Let's do our test statistic. Again, it's p hat. Now in this case here, p hat is 0.26. And our hypothesized proportion is 0.2. Our denominator is going to be the square root of, again, the hypothesized proportion times 1 minus the hypothesized proportion divided by the sample size, which is 1,000. Okay, this is going to be our test statistic. Ooh, pretty big, 4.74. See a test statistic this big, it's well, anyway, you'll see that this is going to be an easy reject the null hypothesis, but let's do it anyway. Go through the motions of doing this. We'll store this into alpha A. Now this is a two-tailed test, two tails. So when we calculate our p-value, we have to multiply 2 times. Now in this case here, notice that 0.26 is bigger than 0.2, so we're going to use the right tail formula for the normal CDF. We have to use 2 times it because this is a two-tailed test. All right, that's because the alternative hypothesis says that p is not equal to 0.2. All right, so we're going to use 2 times normal CDF. And once again, since this is a right tail, we will use alpha there. And our upper will be, we'll just basically use what we have here. All right, hit enter. Oh boy, look at this number here. Now, here's what you have to know about this number here. P-value is not 2.1. These students see this and they think, remember the p-value is a probability. Probability has to be between 0 and 1. So this can't, that 2.1 cannot be the probability. But notice at the very end, it says e -6. E represents an exponent. An exponent to what base? 10. So this is 10 to the -6 power. All right. So this is really 2.1 times 10 to the -6 power. Now, if you were going to do the conversion to an actual decimal, this would be, you'd have 5 zeros, it'd be point, and then 5 zeros, and then 2 1. All right, so it's a really small number. much smaller than our alpha is equal to 0.05. So this is definitely reject the null hypothesis. Okay. All right, this is a case where multiplying by 2 wouldn't have made any difference, but you do have to multiply by 2. You have to show this is your p-value. It's pretty much very close to 0. All right, that's it for those examples. Let's do 2 word problems, and then we'll be done for the video. All right. So we'll go back to the book, and we'll pick a couple word problems. I think I've selected a couple of them. Let me just find the first one, 6.53. Let's look at 6.53. This is the one here. It says left-handed lawyers. Left-handed lawyers. All right. Now, it says approximately 10% of Americans are left-handed. All right, so we're going to assume that is known. Right? 10% of Americans are left-handed. But suppose we're interested in looking at a group of lawyers. All right. I don't know why, but that's what we're doing here. So we're taking, we're looking at the actual population that we're interested in is population of lawyers, and we're taking a random sample of 105 of these lawyers out of all lawyers that are in the U.S. Right. So out of the 105 lawyers, 16 of them were left-handed, or the rest are right-handed, or maybe equal-handed. I don't know, but let's say that 16 were left-handed. So we want to test the hypothesis that the proportion of left-handed lawyers differs from the proportion of left-handed Americans. In other words, we want to test the null hypothesis. Number one is that H naught, or the null hypothesis, is that P is equal to 0.1, right? All right. In other words, the null hypothesis is saying there's no difference between lawyers and the rest of Americans. We're going to assume that initially that the lawyers are just like any other Americans, and therefore the proportion of left-handed lawyers would be 0.1. Then the alternative hypothesis is that P is not equal to 0.1. Notice that the word differs here in this sentence here. Differs means not equal to. So this is a two-tailed test. All right, so 0.1 is our n. Let's just write that down. Let me write down the information that we have here. So we have P is 0.10. That's our null proportion. Now to notice here that they say 16 out of 105 are in the sample are left-handed. So 105 lawyers in the sample, 16 are left-handed. We need to calculate the sample proportion. Let's go ahead and do that. All right. So stop sharing here. And let's go to our all right, we're going to go to our calculator. So let's calculate the actual sample proportion. So 16 divided by 105. I believe those were the numbers. And there's our sample proportion, 0.15238, and so forth. Now, it would make sense in this case here because it's not an exact answer here. There's a lot of digits to the sample proportion. It's to store it. So why don't we store the sample proportion in, well, since it's a sample proportion, why don't we store it in S, which stands for sample proportion, all right? So just so that we remember where we stored it. So I'm going to store this in S, and where is S? I'm looking above all these numbers here. S looks like it is, where are you, S? Looks like it's above the LN button here. All right, so I'm going to do alpha LN here. Here's S. And I'm going to hit enter. So my sample proportion is now in S. So I might as well use all the digits that were given here. And so whenever I need to enter the sample proportion into a calculation, like in the test statistic, then I can do it. All right, now, one thing I do need to do is calculate n times p and n times 1 minus p. Remember, the n here, there was 105 lawyers that are in the study, in the sample. So n is 105. So I'm going to do 105 times n, which is 0.1. That's the null hypothesis. And that is bigger than 10, so that's good. And then we'll do, again, n times 1 minus p, which is times 9. And notice that is well above 10. So yes, we can use the normal distribution. All right, we can use the normal distribution to calculate our p-value. So let's do our test statistic first. Remember, our sample proportion, p hat, is in the letter A here, or letter S, right, in alpha S. So let's now do our test statistic. I'm just going to clear out the screen here, just doesn't affect anything. And I'm going to put in our sample proportion. It's sample proportion minus the hypothesized proportion. I have it in S, so it's going to be S minus our hypothesized proportion is 0.1. And we divide that by the square root. Okay, square root of 0.1, our hypothesized proportion, times 1 minus 0.1, which is 0.9, divided by our sample size, which is 105. Okay, and that 1.789 and so forth is our test statistic, which again, I'm going to put into alpha A. So I'm going to store that into alpha A. Okay. And now, if we go back to the problem, let's go back to the problem. Okay, so let's go back to Wiley plus here. All right. And notice that the alternative hypothesis is going to be that P is not equal to 0.1, right? In other words, it differs from the proportion of left-handed Americans. It's different from 0.1. So we're going to use our two-tailed test formula for p-value. Go back to the calculator. All right. So we're going to use this, of course, for our p-value. So we're going to say 2 times. Remember, it's two-tail. Normal CDF. Okay. And is greater than, we're going to use greater than here because the p hat is bigger than p. All right. So we're going to use this form of the formula. And remember, the p hat is bigger than 0.10. So use the right tail portion of this, 2 times the right tail. We'll scroll down, so it's already set up for us correctly. And there's our p-value, 0.0736. I guess we're round to 4 decimal places. All right, so we write that down, 0.0736. Now I have to go and check what the alpha is for this problem. Back to the book. And the alpha in this case is, well, they're actually giving us 2 possibilities, 5% and 10%. Well, if the alpha is 5%, 0.0736, that's our p-value, is greater than alpha, and therefore we would not reject the null hypothesis. However, if we use a 10% significance level, 0.0736 is less than alpha. So with a 10% significance level, we would reject the null hypothesis. Now, that's kind of crazy, right? But that's what sometimes happens. But the thing is, we have to choose this significance level before we do any research, all right? So it's important that a researcher uses what's typically used in their field of study. If it's sociology or psychology or some other field, education, they all have their standard ways of doing research. And so 10% significance level, maybe they use it, or 5% might be more typical. But depending on which the alpha is, in this case, determines whether we reject or not reject the null hypothesis. Now, suppose the alpha is 5%, then we would not reject the null hypothesis since the p-value is bigger. And we would say something like, at the 5% significance level, there's not enough evidence to reject the null hypothesis that there's no difference between, or actually, I might say it this way instead of saying that. I would say at the 5% significance level, we'll say there's not enough evidence to conclude that left-handed lawyers are different, that the proportion of left-handed lawyers out of the lawyer group is different than for all Americans. We would conclude that there's not enough evidence to show there's just a difference between lawyers and ordinary Americans in terms of left-handedness. Now, if we use 10% as significance level, then we would say at the 10% significance level, there is enough evidence to accept that the proportion of left-handed lawyers is different than for ordinary Americans, okay, in terms of left-handedness. All right, so that's an example, 6.53. I want to do one more question, and I think I'm going to do 6.55. So let's look at that one, and then we'll be done. All right, so let's look at this one. It says, what proportion of college students are satisfied with their overall academic experience? Now, there's a lot of college students in the survey, 5,204 first-year full-time college students in the U.S. were surveyed, right? So all over the U.S. And it was surveyed at the end of the first year. And it says that 4,122 of them, of the students in the sample, said they were satisfied with their overall academic experience. All right, so that's our sample data. It says, does the data from the sample provide evidence that more than 75% of U.S. full-time students are satisfied with their overall academic experience at the end of the first year? Well, now, the first step, of course, is do our null and alternative hypothesis. The null hypothesis in this case is that p is equal to 0.75, right? Because it states it right here. Now, please don't use the data from the survey, because that's done later. We come up with the null hypothesis before we do the research. All right, so null hypothesis is that p is equal to 0.75, and it says, is there enough evidence to show that more than 75% of students are satisfied? Well, that means that the alternative hypothesis is that p is greater than 0.75. This is a right-tail test. But before we do any testing, we have to check our assumptions. Number one, was a random sample done? Well, let's look at it here. It says the survey was done. Survey was administered at the end of the first year, and 4,122 of the students in the sample said they were satisfied. All right. Unfortunately, it doesn't mention that it was a random sample. It should. All right. And don't worry about it. It will, in the final exam, it will in my exam state that the sample was randomly selected. We have to sort of assume it here, but otherwise we can't really do any hypothesis test. All right, so we'll make that assumption that it was a random sample. And the other question is, does n times p and n times 1 minus p, is it at least greater than 10? I can guarantee you it's going to be, but you have to show the calculations. So what is n in this case here? Now be careful. N is not 4122. N is 5204. That's the number of people in the survey. 4122 answered that they were satisfied, but that's not n. That's just the number out of the survey, out of the 5204 that said they were satisfied. So 5204 is n, and our hypothesized proportion is 0.75. All right, so we need to do our calculations first. Make sure we can do the test. So let's go back to our calculator, clear out the screen here. And let's do n times p. So n is going to be 5204. And p is 0.75. I can tell you that's way above 10. 3,903, yeah, obviously. And then we're going to do n times 1 minus p. And what is 1 minus p? 0.25. Yeah. So very easily we can use the normal distribution. So what do we need to do? Well, we have to go, let's go back to the problem. Let's count now. In this case, like the previous problem, the actual sample proportion was not calculated for us. So we have to calculate it. So let's go back to the book. And remember, in this particular question here, 6.55, they give us that 4,122 out of the 5,204 said that they were satisfied. So we need to calculate the sample proportion, and then we will, like we did before, we'll store it in the letter S, which stands for sample proportion. This is something I decided to do. All right, so let's do that. So we're going to say 4,122 divided by 5,204. And our sample proportion is 0.79208, so forth. We're going to store that in our alpha S, right? Alpha S. Oops, that's not right. So I've got to clear that. Store it again. Store. And let's say alpha and S. Okay. I think I used hit the second button by accident there. Hit enter. So that's 0.792 is now in alpha S. That's our sample proportion. Now we're going to calculate, we'll clear out the screen, we'll calculate our test statistic. Again, alpha S minus our hypothesized proportion of 0.75 divided by, and again, we do the square root of 0.75 times 1 minus 0.75, which is 0.25, divided by, now be careful, we have to use the sample size here, 5,204. And hit enter. Oh boy, this is big, very large test statistic. I can tell you we're going to end up rejecting the null hypothesis, but let's just go through the motions here. All right, so this is a very big number here. All right, and by the way, you still have to show all the steps, even if you know by intuitively, looking how big this test statistic is, that we still have to show the numbers. All right, so we're going to do the p-value in this case. Now, remember, this is a right tail test, right? Right tail test. So we'll do normal. Now, one thing we did not do, right? We did not actually. Oops. Sorry about that. We didn't store the test statistic. We have to store it in alpha. So let's go ahead and store it in alpha A. Right. All right. Now we're going to do our p-value, right? So we'll do normal CDF. This is the right tail test. So we'll use this. See, sometimes it's better to use the alpha so we don't have to type in any numbers, as long as you replace the current number you replace the old number with the new number in alpha A. So we could just use this as the right tail test. Enter. Oh boy, look at this number here. 1.19 times 10 to the negative 12th power. This is pretty much 0, right? So the answer is overwhelming evidence here that the proportion is well above 0.75. well above 0.75. The p-value is point, and then you have 11 zeros, and then you have 119. After that, this is pretty much 0 for the p-value. But you would say 1.19, what's the p-value? 1.19 times 10 to the negative 12 power, which you could say is close to 0. And since this is way below any alpha that we could pick, then we're going to reject the null hypothesis. All right, so it doesn't matter whether alpha is 1% or 5% or 10%, doesn't matter. This is going to be a very strong rejection of the null hypothesis. So we would say with, now actually let's go back to the problem here so that we state the problem correctly. Okay, we have to see exactly what the alpha is in this case here. See, they don't even bother with alpha, do they? They don't even give you what alpha is in this problem because it doesn't matter. But you could just say something like, even if we pick 1% as our significance level, the p-value was much less than that. It's close to 0. So therefore, even at the 1% significance level, we would strongly reject the null hypothesis and support the alternative hypothesis that more than 75% of students are satisfied with their first year of college. All right, and that's it. So stop sharing, and that is the end of section 6.1. Once again, when I get back from my trip, we'll go over all of this with you. We'll go over all of it. I'll give you some more examples. There'll be, of course, homework examples too. So what do we do next time? We're going to start 6.2, and we're going to start talking about confidence intervals with respect to means. All right, we're going to be dealing with means, averages, population means, and we're going to be testing hypotheses regarding population means. So we'll be looking at the 6 steps of hypothesis tests for means. All right, and next time, not hypothesis test, the steps for creating a confidence interval for means. We're going to do confidence intervals first. So it'll be 6.2D, where we'll look at the distribution of the sampling distribution for means. And then we'll talk about creating confidence intervals when we want to estimate a population mean using a confidence interval. So we'll talk about that next time. I'll introduce you to a new probability distribution called the T distribution, something we haven't talked about yet, the T distribution, unless we talked about it earlier. No, we have not talked about it because in chapter 5, we dealt strictly with the normal distribution. So this will be something new that I'll talk about next time, the T distribution. And it is important that those of you who have the 83 calculator, there's something I have to update on your calculator. So hopefully you've done that already. If you haven't, I'll talk about it a little bit next time, what you need to do to get your calculator all set for what we'll be doing next. You'll need something there that is not there. And that's just for the 8 people with the 83 calculators. If you have an 84 calculator, you're good to go. All right, but then don't worry about anything I just said. We'll talk about 6.2 next time. We have 2 more recordings. So I'll deal with the distribution of means and then the confidence intervals and this new probability distribution. Deal with that next recording. And then the recording after that, I'll be talking about hypothesis tests for means. Okay. All right, that's it. And thank you for listening, and I'll see you next time.